Sir, it is okay for you? Shall we start live now?
Yeah, sure.
Yeah. Mahesh, please start the live.
Yeah, we
Um,
are live on.
okay, sir, if you have any PPT, you can keep it open.
I have a PPT. I'm already having it ready. So whenever you are okay, I can start sharing it.
Okay. Sure. Okay, sir. So, Aditi, you can start now.
Thank you. Thank you, Jayashree. So, people, today we have a very special guest with us. So, allow me to introduce him to you. So, we have Mr. Sudarsun Santhiappan here with us. Mr. Sudarshan is the Chief Scientific Officer at BUDDI.ai. Mr. Sudarshan did his Master's in Technology in Computer Engineering from IIT Madras and also holds a degree, a PhD degree in Computer Engineering from IIT Madras. Sir worked as a project officer on text analytics and predictive intelligence modeling at IIT Madras. And he is basically an incisive leader with over 2 decades of invaluable experience in leading AI research and development projects for end-to-end artificially intelligent product development, systems, software design, and development in assignments and deputations. A felicitation manager and research scientist with rich and extensive experience in predictive modeling, informed decision making, and big data analytics using statistical machine learning, soft computer methods, and knowledge bases. So I would like to request you all to welcome Sir, and over to you, Sir.
Thank you. So I'll start my screen. Okay. Is my screen visible? Is my screen visible?
Yes, sir.
Okay, thank you. Okay, so the next 45 minutes to an hour, we are going to look into the possibility of exploring a paradigm called functional programming and try to understand why it is a better suit for solving data science problems. So there are popularly two different paradigms today. You can call them as procedural languages or procedural programming. The second most popular one is object-oriented programming. So I'm sure many of you have played with languages coming from these paradigms. But there is a third paradigm. Ideally, it should be called the first paradigm, but for now, let's call it the third paradigm, called the functional programming paradigm. So it has become it is becoming popular now, but the adaptation is not the way it should be because of largely because of the ignorance amongst software developers who have jumped recently into data science. If you look at the data science practitioners of today, most of them have moved from software engineering or they have taken that as an additional role in their jobs. So these people have always been tuned to developing things in object-oriented style, sometimes procedural style as well. And when they want to solve data science problems, they still hang on to the same O programming and procedural programming to solve problems. But there is an ideal programming model for data science problems, and which I think is functional. So today's objective is to understand what are those special needs for which we need functional, and how those special needs are nicely addressed by the functional programming paradigm. So I'm not going to teach functional programming here. We are only trying to motivate the need for functional programming in data science solutions design, because functional programming by itself is an ocean. It cannot be covered in 45 minutes, I mean. So moving on to the topic. So we'll just refresh what we mean by data science. There are a lot of definitions that you can find in textbooks, but the best definition for data science is what you see on the screen. So it's a discipline of study that helps one to embark on a journey from data to decisions, right? So it's a journey from data to decisions. So I start with raw data in my hand, and sometimes my goalposts are mentioned by the client. Sometimes the client themselves do not know what the goalposts are. So as a data science practitioner, we have to figure out what are the possible goalposts towards which we can use this data, put this data to use. So essentially, I have volumes of data. Can I make sense out of these data and maybe translate those insights into something actionable down the line? So that is the primary objective of any data science practice you may come across, right? So essentially, it is a journey from data to decisions. And I'm using the word decisions loosely, but these decisions could mean insights, it could mean reports, it could mean solutions, applications, anything that is tangible, right? That is going to be practically usable. So that I'm calling as decisions loosely. So it's a journey from data to decisions. So in my opinion, data science is not a skill, right? So will you call computer science as a skill? You will not, right? It's a discipline of study. So likewise, data science is a discipline of study. But if you say machine learning, is machine learning a skill? Absolutely. Because machine learning is a toolkit that you carry during your journey from data to decisions. You start with raw data, you use a lot of tools and techniques to transform the data into computer understandable formats. And then once the computers can process the data, you instruct the computer to extract interesting discoveries from within the data. And then you move your journey forward. That's the usual process in any data analysis / analytics kinds of use cases. So machine learning allows one to solve the predictive aspect of data analytics problems. So we can call machine learning as a toolkit that one carries in the journey from data to decisions. So machine learning is definitely a skill, but data science is not. So data science is a discipline of study. It's my training, I can call, and it allows me. I'm sorry, what?
99 लोग हैं अभी इसको लीव कर देते हैं.
Can you please mute yourself? Oh, shit. I'm sorry, if you have a question, please unmute yourself. Otherwise, please remain muted. Thank you. Okay, moving on. So for a given set of business problems, a data science practitioner uses mathematical models and programming to develop solutions. This is what we always do. So we have a problem in hand, and this problem requires some solutions that leverage the available data and translate these data into actionable insights or applications or solutions or whatever. So we need two components. One is the mathematical modeling of the data, because without mathematical modeling, it is impossible to make sense out of the data, because the data is voluminous. So it is humanly impossible to go through each and every data point to make sense out of it. So we have to use mathematical tools and techniques to put the data into use in volumes. So mathematical modeling is crucial for a data science practitioner. So if your practice does not involve mathematical modeling, then I think you're doing something incorrect. So you have to start capitalizing on mathematical modeling to make your life easier. Trust me, with mathematical modeling, your life can become very easy. And essentially, then once you have a model of your problem and solution, and for implementing, you definitely require programming. So you see most of the data science practitioners use programming languages such as Python, largely Python, and a fair share of people use R-like languages to also solve. You seldom see people using enterprise languages to solve data science problems. because the kind of support you get from enterprise languages for data science applications is fairly low. But when it comes to Python and R-like languages, I would say Python, the kind of support you get from the community for solving a specific problem is amazing. So all I have to do is I need to know where to find the solution amongst the available solutions, and probably 70% of my problem is already solved by someone else. All I need to know is find who has solved my problem and just connect the dots. So usually a data science programmer, a developer who's solving data science problems, majority of your time is spent in hunting for an existing solution. I mean, ask yourself, you'll be doing that. That's not a bad thing. I mean, if it is already there, why not use it? So I definitely welcome reuse of solutions. But when we use someone else's solutions, number one, we should give credit to them. Number two, we should take utmost effort to understand the solution, so that we know the limits and bounds of the existing solution, because ultimately you are going to be responsible for anything happens, right? Not the person who supplied you the source code. So you are going to be responsible. So it is better to understand where you borrowed that piece of code. You have to understand what is the piece of code you have borrowed, so that you can handle the questions later from your customers. That is also a good practice to understand what we borrow from. Okay, so moving on. So the general pipeline of data science has largely these 4 functional blocks. We're not going into the details of these functional blocks. Just to understand the journey from raw data to decisions, the first block is the place where we acquire data in its raw form. And the final product, the last stage of the pipeline, is where it translates into something tangible, something usable, and something for which a customer is willing to pay some money, right? So the journey, I mean, in the example, in the picture that I'm showing on the screen, there are only 4 blocks, but in reality, you may have 100 different blocks. There are a lot of moving blocks in the pipeline. Abstractly speaking, largely 4 big blocks. Third block is the most interesting block. This is where all your real data science practice come into play, or machine learning practices come into play. So yeah, the journey from data to decisions. Now, let's look at some of the interesting traits of a data science problem in general, right? So the idea is, we want to understand, are there any peculiar characteristics of data science problems? If we understand these peculiar and interesting characteristics, we may probably leverage them for our benefit, right? So we are used to some style of solution implementation. And if we understand some very interesting peculiar properties of a data science problem that I'm trying to solve today, can I leverage it so that I can come up with a better solution, a more elegant solution to solve the problem? So that is the general idea. So there are some very interesting traits. So if you look at data science problems, most of the tasks, I mean, at the finest level, you will see the tasks are very, very small in nature. For example, let's say if you are cleaning your data for zeros. Let's say I want to get rid of all the zeros and NAs, not available data points from my data. So you might be you calling some functions in your data frame to do that. Let's say fill NA or replace NA or remove NA or replace zeros. Some functions are already available in any library that you may use to solve the problem. But the characteristic that we are interested here in is the task is very small in nature. And there are a few who have not muted themselves. Can you please mute yourself? There's a lot of background noise coming through. Thank you. So these tasks are very small in nature, but these tasks are expected to run on all the data instances. So when a task is expected to be run on all the data instances, then you can straight away imagine the computational requirement, the computational power that is required to run it, right? So let's say I'm going to run this particular task in a laptop of mine, and if I have to run this application in CPU, then it automatically gets sequentialized, and I have to finish all the data points running through this simple task, and it is going to take a proportional number of seconds to get the task done. But what if I can run the task parallelly across multiple CPUs? So what is the constraint that we need to have? So the constraint that we need to have is that the task has to be data independent. For instance, let's say I am getting rid of all zeros from my data set. Or let's say I am, let's say I have a bunch of strings in my data set, and I'm just stripping all the spaces from all the strings that I have in my data set. So stripping the spaces from one string is independent of stripping the spaces from another string. The task is stripping, and the stripping task has to happen on all the strings that I have in my data set. I may have a billion strings in my data set. I have to run this stripping task on all the data points, essentially the strings, and I find that the task run on one data instance is independent of the same task run on a different string. So when the task is data independent, it immediately opens up an opportunity for me to parallelize the task run. So if the function, the task can be referred as a function, this function or a procedure, whatever we want to call it, this function appears to be data independent. So can I run the function parallelly across all the data points? I mean, in principle, let's say if I have 1 million data points, in principle, I can run the task in parallel across 1 million data points as a 1 million thread application. It should be possible, but it should be possible in theory. But for all practical reasons, you cannot spin off 1 million threads. That would be really atrocious. So what is the next step? So what I can do is I can probably partition the data into, let's say, 10 or 15 or 20 number of partitions, and maybe deal the data parallelly in partitions, so that I can leverage the available CPUs to run the tasks in parallel and get the end-to-end time shrunk by 1/16th or 1/30th, depending upon the number of CPUs that are available with me, right? So the moment the task becomes data independent, which means it is not sensitive to the data, running the task in one data point is not going to disturb running the task on a different data point. If that is the case, then immediately parallelization opportunity opens up. But as data science practitioners, we don't really care about parallelization until it bites me in terms of running time, right? That's the usual thing. We don't care about parallelization. We don't care about multi-threaded application. We don't care about distributed computing until it bites me on the runtime. So if the runtime is very long, then I am motivated to think about how can I divide this task into smaller subtasks and solve them in parallel. But if my application is running really fast, I don't have to worry about parallelization, isn't it? So that is why most of the Python programmers don't leverage multiple CPUs. They always run in single CPU. I mean, if you look at the running style of Python applications, you will see that the CPU is only 100%. You may have at least 8 or 16 CPUs even in your laptops, but you don't seem to leverage the available CPUs, because to leverage the available CPUs, the programming style has to be different. See, I am used to writing Python code in object-oriented style. Object-oriented style does not encourage me to parallelize my data because of the very design of object-oriented programming. See, object-oriented programming mimics how humans talk to each other, how humans collaborate with each other to get a job done as an individual or as a team. I mean, OO does not involve machines into the play. OO only thinks about how humans operate. I mean, how you can solve a problem in a humane style. That is the strength of object-oriented programming style. But I would call that as also as the disadvantage of OO style, because it is not allowing me to leverage the hardware in a natural way, in a native form. All right. So it's a limitation. But the opportunity is there. When I know my task is small, when I know my task is data independent, when I know that I have available CPUs, I have to parallelize my tasks and leverage all the available resources to finish the task faster, right? Okay, so the last very interesting trait is that, we have two different stakeholders here. I mean, I'm personifying data as an individual here. So you have a method or a task, and you have piles of data. So there are two different stakeholders here. The general idea behind computation is data has to go to the method, isn't it? So we always move the data to the function. We don't move the function to the data. We always move the data to the function. So we have this concepts like pass by value, pass by reference, pass by pointer. All of these are meaning passing the data to the function. But should that be the case? Can we not do it in a different style? See, when I have large volumes of data and I have my function to be very small, it does not make sense for me to move piles of data to that small function. It makes more sense to move that small function to the pile of data, because it's very convenient, isn't it? So data movement is very expensive because of the volume of the data movement is very expensive. But the method movement could be a radical change in the way we execute our solutions, right? So the fourth interesting trait of data science problems is data science problems prefer you to move the method to the data instead of moving the data to the method. These four traits, just remember these four traits. We will connect the dots in the last but one slides. So let's see some examples of these traits and see how we can do them elegantly. So I'll take one. The first use case is I want to filter data. So I have data with me, and I just want to get rid of some data from the available data set based on some constraints, right? So filter a data frame based on constraints. So here a condition is applied on every data instance. The result of the condition check on the data instance is, as usual, independent of the same check running on other data instances. We know that the task, which is a filter task, is independent. So if I'm checking for zeros in my data set, I'm checking for, let's say, negative values in my data set, checking minus, let's say checking on -3 is independent of checking on +44. The results are not going to change, right? If you check -13 to +13, the results are not going to change. They are independent of the data. The filter operation itself is independent of data, right? So let us see how we can frame the solution. So once we are aware that the independent of data behavior is present, then we have to look for parallelization opportunity. So let's, as a practical example, look at filtering non-positives from a random integer array. So this small code snippet allows you to generate 1000 random integers in the range 0 to 10,000. So this code block will generate that particular array. I mean, of course, there are more elegant ways of generating random numbers. This is one way of generating random numbers. But time complexity ways, both of them have the same time complexity. So there's no benefit in doing in a different style. So this is how I usually do. So I have an input array, right? An array A with 1000 elements randomly generated in the range 0 to 1000 or 10,000 or whatever, right? And I am trying to get rid of non-positive numbers from this random integer array. So the way we frame the solution is that we create an output container, an output blank array, and for every element in the input array, we run a condition check, which is the element greater than 0. And if the element is greater than 0, you append the selected item into the output array. This is how usually we frame it in a procedural style. This approach is procedural in nature, right? There is no O involved here. This code block is definitely procedural, right? And can we do this any better than how it is done in a for loop? But look at this way of doing it. So the entire solution became one line, and the task is the same. What we did is, instead of doing an if condition, we just changed that if condition into a simple Lambda function. So Lambda function is a function without a name, right? It's a function, it's a nameless function. And the lifetime of a Lambda function is within the scope, within the scope of where it is being created. So if you look at this particular example, I hope my mouse pointer is visible. If you look at the scope, this Lambda, this is the function, right? The scope, the lifetime of this function is only within this parenthesis, this inner parenthesis. This function does not exist anywhere else. It exists only within this space. So this Lambda function, what it does is, it is framed using a method called filter. Filter is a ready-made method in Python, and filter takes in an array-like data structure as an input. Here we are passing the array, and filter runs the Lambda method that is supplied as the first argument on every instance of this array-like data structure, right? So if you look at it, so here also we are doing the same thing. Assume this is the Lambda function, which is evaluating the value to be greater than 0 or not. And when the value is greater than 0, or the function is evaluating to a true, then the output gets appended here, right? This is how we framed it in procedural style. But look at this style. What we are doing is we are calling a standard method in Python to invoke a similar behavior, but instead of passing the data to the method, which is the constraint, see here we are passing the data. So this is where we are iterating over the data, and the data is passed to this condition I greater than 0. We are passing the data to the condition, right? In this method, we are passing the method to the data. The data is here as the second argument. The method is the first argument. We are passing the method to the data, and this function will automatically execute this Lambda method on every instance of the incoming array, right? So the way it is, the way this construct is implemented will be very similar to the for loop only. But from the programmer's point of view, the style with which you visualize data movement has changed. See, I'm not saying that the moving functions to the data or data to the function. If you look at the final implementation, let's say if Python interpreter translates the code into a bytecode and then bytecode to machine code, and if you look at the way the machine code gets executed in the function move to data versus data move to the function, the final execution will be very similar, right? Doesn't matter. But the point is, at the programmer's level, the abstraction is completely different. The way we abstracted the problem, the way we abstracted the solution is completely different. See, the visible advantage that we have here is the code block has become one line instead of 4 lines. Straight advantage. This is a naive example, but there are a lot of excellent examples where you can see several lines of code might shrink to one single line if you rewrite the logic where from moving data to method into moving method to data. If we reframe the way we design the solution into moving the method to data, you will see that your code block shrinks drastically, and it becomes very cryptic and also very elegant. Because the shorter the code, the cooler the codes. The cooler the code gets, and it's a pride to write cool code for any developer. It should be a pride for any developer to write really cool code, right? So this style of executing, this style of creating solutions, right? Although at the final running level, the behavior is going to be similar, but when you see the code, it looks immediately beautiful. It looks immediately beautiful, and it looks smaller, it serves the purpose, and it is less error prone. That's this brilliant advantage you get. Because where can you make a mistake here in this single line? If at all you make a mistake, you can make a mistake on the Lambda function. Everywhere else it is perfect. It is perfectly crafted. Whereas in the function block, if you have not initialized your input array, we get dinged. If the condition is not well designed, or if it is not well framed, we get dinged. If the for loop is not set up correctly, we get dinged. And the way you extract the output and populate to the output array, here also we may get dinged. So the possibility of errors is more in the procedural style, whereas in this style, the possibility of error is fairly low, because you don't have an opportunity to make a mistake, except for defining the Lambda function totally wrongly. Right? So here, what we have done is we have moved the method or the function to the data, and the standard function filter is executing this particular Lambda function on every method. Wherever this Lambda function has succeeded or it has written true, those elements get collected by the output. Automatic, everything, the pipelining is automatic. I don't have to set up an output array. I don't have to call append method on it. All these are boilerplate. All of these are boilerplate code. So this style of moving the method to the data cuts the chase and gets me to the result perfectly. Right? So the second beautiful advantage of this kind of framework is that it ensures that the input stays immutable. Of course, in this example, I have overwritten the same variable again, but if I have chosen a different variable here, A stays immutable, which means the values in A remains the same. So the basic idea of moving the method to the data ensures that the incoming data stays immutable. So immutability of the data is very important, because when the data is immutable, only then we can guarantee that data independence condition. If you can, the moment data independence condition is guaranteed, then parallelization is immediately possible. But the moment we make the data mutable, which means my arrays can get edited, can get modified, parallelization option goes away, immediately goes away. Even if you force the program to introduce parallelization, the efficacy of such a parallel implementation will be miserable if you allow for mutable data types. So parallelization works like a charm with immutable data structures or immutable data containers, because it is tuned nicely when you deal with immutable containers. Okay, so I hope you got the crux of it. We'll take one more example. The second example that we want to talk about is finding the max value. This problem has one issue. The issue is this problem has data dependency problem, because the maximum value of an array is dependent on every data point, isn't it? So the maximum value of an array is dependent on every data point. I cannot execute the maximum value finder in a data independent style. It is impossible to do that, because the very definition of max value is maximum of all the values in the array. So it is the method, the task itself has inherent data dependency constraints. So how can we solve this problem? So how can we overrule this deterrent? This is a limitation, because I want to compute the maximum value of an array. And if my array is 10 billion data points, and if I have to find the max value every time, then I have to scan through all 10 million data points to get it done. It's an order n algorithm. Problem for me. But let's say if I have 100 CPUs, can I bring down that order n to order n over 100? Is that even possible? So that is something I want to understand. So what we'll have to do here is to transform the problem into a
finding max value anta ఇంటికి బ్రైట్నెస్ కూడా తగ్గిద్దాం ఎందుకు
Mais rápido.
Adri, is there a possibility to mute all? See, random people wake up and they disturb, man, seriously.
Okay, I would like to request you all, please mute yourself. Okay, if you have to ask questions, we can take it in the last of the session. Please cooperate.
No, I don't think they are doing it on purpose. I think it is accidental or something. So if you can mute everybody, that would be great. I think you have the option, right, as a host. I think you have a,
Sorry, sir. Probably it's not me who's having this option
okay.
to mute everyone. I'll just check it out, sir.
Yeah,
So you
sure.
please continue. I'll just check it out.
Okay, thank you. Okay, moving on. So we have a problem in hand. That problem is not naturally dependent. And thank you. So this problem is not naturally data independent. So we have to do some small jugaad to introduce data independence condition. So here, this is what we will do. So what we will do is we will split the data into different blocks, let's say partitions, and then deal partitions parallelly. Let's say if I have 10 billion data points with me, and if I divide this 10 billion data points into 1 billion blocks, and maybe estimate the max value across okay. So estimate the maximum value per block parallelly, because finding the max value in one block is not going to disturb the max value in another block. So what we will end up getting is we'll get the max value per block, right? So let's say since we have 10 blocks, we will have 10 outputs. Now all we have to do is find the maximum of the block level maximums. So that can happen in a sequential style, no problem. But I'm changing the data dependency problem from 10 billion data points to only 10 points, while executing the maximum finder across 10 partitions in parallel, right? So if I have more CPUs, then I can split it into 100 partitions. If I have even more CPUs, I can split it into 1000 partitions. If I have a proper management of thread management, then I can create several thousands of partitions and deal them one by one sequentially to find the maximum values, but use all the CPUs all the time. So it's all possible, right? So what we say is, when the problem is inherently data dependent, we can transform the problem into some other form where you can get the data independence condition at least on a partial basis, and still be able to leverage that benefit to run things in parallel, right? So the goal for dealing with large amounts of data is to think about the opportunity for how we can parallelize the processing, right? That should be the mindset of any programmer. That is how they should think. So if they are dealing with the same task across a lot of data points, and if they're thinking that they are waiting unnecessarily for the tasks to finish, so find opportunities for parallelizing this task. So let's see how this can be done. So now, as usual, we will generate a random data set, a random array of integers, 1000 integers in the range 0 to 10,000. Then the way we find max, it's a trivial, naive logic to find the maximum value. So you just scan through each and every element and find out the maximum value. This is what we will do. And this is a order n time complexity algorithm. We cannot do better than that. That is the best you can do to find the maximum value for a given array of size n, right? Now, what we are proposing is we will convert this into a function, but this function will operate on a partition, not on the whole data set, but it will operate on a partition. So if you look at it, it takes a partition as an input, which is essentially another array, and it does the same logic, which is here. It applies the same logic on the partition. That's all. There's nothing fancy here, right? So let's construct a function of this type, and then we invoke another method called map. I'll explain what that is. So what we are saying is, we have a function which can find the maximum value given a partition of data points, some partition of data points. that this function can estimate the maximum value. So what we are doing is we are creating the partition ranges. So what I'm doing is I'm creating 5 partitions because there are 1000 data points. I'm creating 5 partitions, and these partitions are identified by this particular range. So we say 0 to 200, 200 to 400, 400 to 600, 600 to 800, and 800 to 1000, something like that, right? And then what we say is we take these parts as an input and run the Lambda function across all the partitions. So this construct that we have here, tells a runtime that these partitions are data independent. They are data independent, and the map job, essentially what happens is it runs this Lambda on every partition coming out from the incoming array. That's what it does. Okay, so if the map job senses that the data that is being processed has the data independence property, if the compiler allows, the map job can be executed in parallel. So Python does not do it automatically, but languages like Scala does it automatically. You don't have to even tell the system to run it in parallel. Scala compiler, what it does is, Scala is a language which it's a JVM language. So Scala runs on JVM. So Scala, what it does is it's a purely functional programming language. I mean, it allows O also, but it is well done when you do it in functional style. So if you create a map job in Scala, and if the compiler senses that the map job is running on data independent blocks, then the runtime automatically spins threads to run the map job in parallel, depending upon the number of available CPUs. You don't have to worry about thread management. You don't have to worry about synchronization. Synchronization is not needed because it is a data independent block. So no need for synchronization. But the spinning of threads, creating the threads, executing the threads, managing the threads is all done by JVM automatically, triggered by Scala runtime. Beautiful language, amazingly designed language. I fell in love with that language when I started learning it 7-8 years back. Just fell in love. Such a beautiful language, right? So Python is kind of caught in the middle. People don't understand what type of language Python is. Is it a procedural language? Is it an object-oriented language? Or is it really functional in general? I mean, it's a confusion, I would say. But most of the Python developers, most of them are still adapting to the procedural style of Python. So all the examples that I've given here, these are all procedural examples. No at all here, right? So Python is better done in OO style, and Python has very limited support for functions, very limited support for functional programming. But we cannot blame it because the language evolved like that. It is basically a reactive way of evolution. Python evolves reactively. But Scala, on the other hand, it evolved as a very mature language, very, very mature language. So I would insist to take up Scala as your enterprise language choice if you have that leverage. Okay, going back to the point. So we are looking at this map function. This map function allows one to run the Lambda automatically on the incoming array. And if the runtime allows, this job can happen in parallel. Same construct, identical construct. We can, if you execute it in Scala language, it will run it in parallel. If the data is larger, I mean, for smaller data, it won't trigger. But for larger data, it will automatically trigger multiprocessing or multi-threading. So in Python also, I remember seeing some package which allows for spawning map job in parallel by using a different function. Instead of map, you will use a different function, and that will also trigger a Lambda on a particular data point, but it will ensure that it handles the map jobs in parallel across threads, across CPUs, right? Those kind of libraries I've seen, but those are third-party libraries. The native Python language does not support parallelization in an automatic style. If you spawn, if you trigger multiprocessing or if you trigger multi-threading, then it is a possibility. But the idea is, this style of programming allows for the compiler to make a choice between sequential execution versus parallel execution. But if you write the same code in procedural style, you're not giving the runtime any choice. You have to execute it in procedural style. That is why I'm insisting on exploring the other paradigms for creating solutions, even for simplest problems such as finding the maximum value. Okay, so moving on. So between these two implementation strategies, what did we do differently? So we use Lambda functions. As I said previously, Lambda functions are functions which do not have a name, and their scope is limited to where they are created and where they are destroyed. So most of the times their lifetime is within parentheses. Sometimes their lifetime is within curly braces, right? Their life is only limited to only those scope. So you create a function on an as needed basis and be able to run that function in parallel style, in sequential style, is up to you. But lambdas are very, very useful. So lambdas are also there in Java language since 1.8. And now they have even more fantastic implementation of lambdas in the modern versions of Java. But Scala has been having it since beginning. It has been having it. So lambdas are something that we tried. And the second unique thing that we did is we moved the function to the data instead of moving the data to the function. That is the biggest difference that we made. Okay. So we also constructed our solution in a style that allows for parallelization by a suitable runtime. So Python runtime is not that powerful, but there are other runtimes which can look at the opportunity for parallelization and automatically trigger parallel processing abilities and execute the function or execute the task very, very fast, right? That opportunity opens up only when you change the way you code, change the way you conceive your solution, change the way you abstract the design of your program, right? So we'll have to think slightly differently to facilitate the runtime to do better job. That is exactly what we are trying to do here, right? So the very interesting sideburn outcome is your code becomes elegant, it becomes short, and you can be proud of it. See, writing lengthy code is always seen as a negative, right? Let's say if someone, okay, it's a double-ended sword. So even in interviews, people ask me, how many lines of code have you written in your life, right? This is a standard question many interviewers ask. But for a given problem, for a given solution, can you write shorter code? Can you write it as short as possible without compromising on quality, without compromising on speed? Can you write it? If you can write shorter code, people are going to look up to you as amazing programmers, because writing shorter code requires a lot of experience, a lot of practice. And the style with which we are attempting to write allows you to write shorter code natively. You don't have to do anything fancy. Just writing the code in that style itself will make your code block as small as possible. Okay, so far whatever we have seen apparently is the way functional programming is implemented or functional programming is practiced. So moving the data, instead of moving the data, moving the method to the data is the very idea behind functional programming. And solving the problem using smaller functional blocks is another biggest trait of functional programming, right? And whenever there is an opportunity for whenever the method is data independent, trigger the opportunity for parallelization. This is a native setup in functional programming, right? So what we see is the interesting traits of data science problem are the basic features functional programming allows you to do. So you just have to marry them. That's it. That's the natural way of looking at the solution, looking at the opportunity, connecting the dots, right? So let's take a step back and understand what is the meaning of a function in a functional programming, right? So a function maps data from the input domain to the output range. This is a standard definition. All of you will be knowing it already. A function takes some input and returns some output, right? So the input is called the domain and the output is called the range. I mean, the family of inputs is called the domain and the family of outputs is called the range. So a function maps a domain to a range. So that's the very definition of a function mathematically and also in programming world, right? In the mathematical world, a function can return only one value. Even in the programming world, it can return only one value as the output. But what you can do is instead of having one value, it can output a tuple. I mean, this tuple can have, it can also return an n tuple. It can have several components, but there is only one output. I would say a compounded output. But functions can take functions can take multiple inputs, but they always generate one output. So it's a basic definition of a function. So the domain and range are usually represented as sets. In majority of the programming problems, these sets are finite in nature, right? Let's say if you're writing a function for finding the length of the string, right? In this situation, the input domain is a string and the output range is a number. But this is an example where the inputs can be from an infinite set, because any string that you pass, the function is going to return the length of the string. And the output can also be from an infinite set, because depending upon the length of the incoming string, the output length can also change. So length of a string is a function that has both input set and output set. Both are infinite sets. But for example, let's say you are trying to find out whether the input is matching a particular keyword, right? The input is matching a particular keyword. So let's say you are looking for stop words. You are looking for stop words in a text. So a stop words is a finite list of words. And the words that you can get in your input function is also finite depending upon the data set that you are using. So we can frame the problem into a constraint problem where the sets can be bounded. It can become finite, right? So majority of the problems that we deal in the programming world, we can find a finite set equivalent of the domain and range of a function. So that's not the point I'm trying to build. Just allow me one more minute. So there are three different types of functions. Just know the names if you have not heard them. So that the first type of function is called injective function. It's also called one-to-one mapping. And there is another type of function called surjective function. This is a many-to-one mapping type problem. And bijective function, it's also one-to-one. It's a combination of both injective and surjective. So essentially what we are looking at in these types are that if the function is injective, it means all the data points in the input set are mapped to a unique data point in the output set. That's why it's called one-to-one mapping, right? All the data points in the input set have to be mapped to a unique point per input point in the output set. But the caveat here is you can have some data points left out in the output set. If you look at here, so 1, 2, 4, 5 are mapped, but 3 is left out. So injective function only cares about one-to-one mapping. It does not think about if there are elements in the range. It doesn't care about that. Surjective function is an interesting proposition where the number of all the values in the range will have a mapping for sure. It has to be guaranteed. All the values in the range, this is the range, this is the domain. So all the values in the range have to have a mapping. So if the function, this particular set cannot be called surjective because 3 is left out. Here we have 3 elements, 1, 2, 3, all of them are mapped. Here we have A, B, C, D, all of them are mapped. This kind of a combination is called surjective, right? And the third combination is we have equal number of inputs and equal your inputs and outputs are equal and every element is uniquely mapped. So it's a combination of both injective and surjective. That's called a bijective function, right? These are types of functions one has to be aware of because they have some unique properties which can be leveraged to your benefit. So moving to the most important aspect, how are functions treated by common languages? So functions are treated as building blocks in procedural and object-oriented programming paradigms. Right? You know that, right? So in the object-oriented world, functions are called methods, and methods have to perform a task on incoming data. So that is what it is done. And they are methods which could be class methods. They could also be methods coming from an object. Seldom, if a language is purely object-oriented, it will not allow you a free function. I mean, it will not allow you a global function. Like Java-like languages don't allow you to create free functions. Python allows you to create free functions. It allows you to create class functions. It allows you to create functions of an object. That's why I said Python is a confused language. I mean, it does not know where it is going. I mean, it just reacts to the market needs and they come up with new versions. It's another interesting way of looking at how programming languages evolve over time. But Java-like languages don't allow free functions, no global functions possible. Every function or every method that you write has to be contained within a particular class. So you only have objects, and you have objects, the methods can be accessed through only objects. That is how Java language is designed, because Java is supposed to be a pure object-oriented language, right? If you look at languages like C++, it allows both. I mean, allows free functions, it allows functions as a part of classes also. Languages like Scala also allows everything. I mean, it allows free functions, it allows functions of functions, it allows class functions, practically any combination of or any treatment of functions you can find in languages like Scala, right? But the general idea is functions are treated differently by procedural and object-oriented languages. They are only seen as code blocks. They are seen as only code blocks. That could be a problem, right? Because functions are treated as procedures or blocks by the compilers, and they are always treated as code blocks. They are not seen as data. They are only seen as methods. So the way Java classes are defined as, okay, a class is made of properties and methods. Properties are essentially data and methods are essentially functions. Right? The treatment is straight away said the black and white difference. They are two different things. They cannot be anything else. They have to be black and white different. So that's how procedural languages and OO languages treat functions. But is that the way they deserve to be treated? We'll see. So there are functions that allow for functions to be sent as an argument. So when a function is supplied as an argument to another function, and when a function can return a function as an output, those functions are called higher order functions. But still, functions are treated as third-class citizens, right? So C uses function pointers. It's an awkward way of calling functions. And Python, Java, C++ like languages use function templates to invoke methods, to pass methods and invoke methods. But let's see why functions should be treated as first-class citizens. So consider an example of this type. Let's say I want to find the factorial of a number, right? So mathematically speaking, n factorial is defined as n into n minus 1 into n minus 2, blah, 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 multiplied by 1, up till 1. This is the definition of factorial. And factorial of a number, naturally looking at it, it is a function, right? We treat it as a function. And if I supply n to it, factorial of n will compute me the n factorial value. So this should be a function. This is my common sense. But let us see if we can think about it in a completely different style, right? So when we implement this as a function, you have two ways of implementing it, recursive style and iterative style. But they will serve the same purpose. One is better in some scenarios, another one is better in other scenarios. But for factorial of a number, the primary problem is the overflow, because the n factorial grows very, 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 very fast. So if you compute factorial of 50, 60, 70 and all, then the number becomes very, very large, becomes unmanageable. But depending upon the implementation, they have their own pros and cons. Okay, so here we are looking at the function implementation of factorial. Now I'm going to make one assumption. I'm going to make an assumption. I'm going to assume that my experiment does not require anything more than 10 factorial. I'm constraining the problem to a finite problem. See, factorial of a number is an infinite problem in principle, because any positive integer factorial is defined. right? It could be a crazy large number, but it is defined mathematically. It's sound. But for all practical reasons, I want to limit my scope to only 10 factorial. Up to 10 factorial is all I will care. I will not need anything more than 10 factorial. Now, if this is a situation, can we change our strategy? Can we change the way we look at the factorial computation as a function? So let's say I pre-compute the values of factorials for all the required values. From 1 to 10, I have pre-computed the values of factorial, right? So if I have it pre-computed, should I still be invoking it as a function? Can I not look at it slightly differently? Can we not construct factorial array or a factorial dictionary to solve the problem by pre-computing the values? Just think about it for a minute. See, instead of defining a factorial function, which is meant for solving the factorial for any arbitrary number, any arbitrary integer number, right? Although it will work for my problem, which is constrained to a maximum of 10, but it is an overkill. But what if I translate this problem into a lookup table problem, right? Because I have only 10 values to be dealt with. And can I not construct this as a lookup table problem and consume this as a simple array? Why not? Just think about it for a minute. So if you look at it, so factorial as an array, just look at it. This is an array. Sorry. So factorial as an array we have, or we can also construct factorial as a dictionary. And then when I want to find F3, just look at factorial of 3 or F7, factorial of 7. This is way faster compared to invoking a function. It's way faster compared to invoking a function. So essentially, if you take a step back, you will see that every function can be mapped to a dictionary. Every function that you can think of can be mapped to a dictionary. Of course, for practical reasons, if the function is going to only deal with finite sets, then it can definitely be translated to a dictionary. But we have been using dictionaries as first-class citizens, first-class data types. And if I don't call, if you don't make functions as first-class citizens, then it is called double standards, in my opinion. So functions are essentially associative arrays. They are essentially associative arrays. For an input, there is an output. It's a dictionary. It's a map. It's a map, right? It's a hash table. I mean, however you want to call it. I mean, Python calls it dictionary. Java calls it hash table. You can also call it as an array. In this case, it can be an array because the inputs are contiguous. But if the inputs are not contiguous, then you cannot construct an array. You have to only construct a dictionary. So that's why I say a function in reality, when the function is dealing with finite domain and finite range, it can be easily equated to a dictionary. So that is why functions deserve to be first-class citizens. It has to be treated at par with any data. So I don't want to talk about here are the methods, here are the attributes. No way. It should not be like that. Because the methods that we have are essentially dictionaries. So they have to be treated at par with any data type or any data structure that we are going to deal with. So languages like Scala brilliantly does this, brilliantly implements this feature. They treat data, they treat functions as identical. If you have an array versus if you have a function, they treat them at par. So in the world of functional programming languages, functions are first-class citizens. Much like arrays, much like integers and floats and strings, they are all first-class citizens. Of course, in the languages like Scala, XML is also first-class citizen. XML as a semi-structured data type, that is also a first-class citizen. JSON is a first-class citizen, right? So, can you please mute yourself? Please, thank you. Okay, so we have understood that functions are nothing more than associative arrays, so they deserve to be called first-class citizens. So now comes the most interesting part, which is movement of data and method. So there is this proverb which says, if the mountain wouldn't come to Muhammad, Muhammad should have to go to mountain, right? It's a very popular phrase, So the equivalent, the way it is interpreted is mountain has piles of data, Mohammed has the ability to process the data. So that is how you have to visualize it. So in our example, mountain is the data and Mohammed has to be seen as the function. So when the data cannot go to the function, naturally the function has to go to the data. That is what we have to always we should do, because that's the best we can have. So let's see that as an example. So look at this simple class, which is basically a class for generating class for having random arrays. So if you look at this constructor is creating n random integers internally, right? And it has two methods. These methods don't do anything. The methods accept another incoming method to perform something on the actual data. So that is how this class is constructed. So this is a class. This is an object-oriented code, but it is constructed in functional style. So it is leveraging the advantage of OO and also leveraging the advantage of functional programming, because it allows for functions to be executed on the array. So it allows for moving the method to the data, right? So this is how this function is implemented. It has a map method and it has a filter method, and it invokes the Python standard map and Python standard filter to execute the function on every instance of the class array, the internal array representation, whatever that we have. So look at the way we will use it in our execution, in our application. So this is a class which will be part of the library, and this will be the part of the main code. So in the main code, I create this object, which is a data instance, and look at this line. This line says out equal to mra.map lambda is being passed as an argument. So here, this map method is only accepting a method as an argument, and this method is executed on every data instance contained by MRA. My random array, that is the MRA. So this is a classic example of method going to the data. So here I had to implement this class to show you this example, but languages like Scala has everything pre-implemented in this style, in this pure functional style. So you can pass methods practically to perform different tasks. So I'm sure you would have heard about the map reduce construct. It started in the Hadoop world 10-15 years back. But it is no longer map reduce, right? I mean, you have a lot of possible functions besides map and reduce. So you have filter, you have fold, you have shift, you have slide, lot of possibilities on the data set. So if you want to understand the fullest power of functional programming in large scale data processing, look at Spark. Look at the way Spark manipulates data with functional programming. And by the way, Spark was implemented in Scala. Of course, Spark has this Python version also called PySpark, which is a front face for the Spark runtime, but the entire framework itself is implemented in Scala. And this framework has been proved to be several hundred times faster than Hadoop, only for the simple reason they changed the way data moved. They changed the way data moved. They stopped moving the data to the method, rather they encouraged movement of the method to the data, and all the time, always in memory. So everything became super fast. Great. So to summarize, so functions are just similar to dictionaries. We have already established that. So they are technically called associative arrays. So much like passing an array as an argument, we may pass another function as an argument. And when you do so, the function that is receiving another function as an argument is usually called the higher order function, because it is taking a function as an argument and it is returning a function as an output. So this function is called a higher order function. Right? In modern languages, functions are first-class citizens. We have already discussed that. And so the definition of functional programming, this is textbook definition. So this is a style of building the structures and elements of computer programs that treats computation as an evaluation of mathematical functions. So that is how this name came into play, right? And functional programming, by the way, is one of the most ancient programming paradigms. So this was existing even before O existed. right? And functional programming style of solving problems is by using smaller functions to compose larger functionality. So they call it function compositions. So you build a functionality with several functions by combining different functions in clever forms to achieve the final functionality. So everything is done using functions in functional programming. So I'm definitely pushing you all to explore FP, especially languages like Scala. You will start loving the way things happen there. So elegant, so beautifully crafted, right? And functional programming is the closest approximation to mathematical modeling. So we said there are two aspects to data science solutions. First is we'll have to mathematically model the data. Second is we'll have to programmatically implement it. But functional programming allows you to do both. Whatever mathematical modeling that you can frame in your mind, you have an equivalent of that in your code as well. Functional programming allows you to do that. But if you have to do the same in O, you will have to do this. You'll have to go around your head to touch your nose. So complicated. It's not the native way of solving data science problems. O is not the native way of solving data science problems. FP, functional programming, is the native way to solve data science problems, right? So this was invented a very early time, during the early times, and functional programming is very close to mathematics because mathematicians created it. So computer scientists used to be mathematicians originally. Now computer scientists have diverged a lot, but in the olden days, computer scientists and computer engineers were essentially mathematicians, and mathematicians created functional programming paradigm. So that's why it's very close to math even today, and it is very relevant to solving mathematical problems. So now we will just try to connect the dots. We saw a similar slide in the past. We said these are the traits that data science problems have. Many tasks are small, but operated on the whole population. Many tasks are data independent. Many tasks are parallelizable vertically and horizontally. Moving the task to the data is better than data movement, as data movement is very expensive. So if these four constraints are my deciding points, then let's see how functional programming cooperates with these 4 points. Yeah, will it allow smaller tasks? Yes. Will it leverage data independent tasks? Yes. Is this parallelizable vertically, horizontally? Yes, very much so. And moving the task, the data movement versus method movement, functional programming allows you to do that as well. So when all the necessary constraints are met, so the natural next step is to adapt to functional programming paradigm and make the best use of the available solutions, so that the code that we create is elegant and you are very proud of what you wrote as your solution, right? So as developers, we should relax our rigidity to embrace the best approaches to solving problems efficiently. I know functional is a new thing for many of you, but if you relax your rigidity a little bit and then just test the waters. If you like it, hang on to it. If you don't like it, no problem. But don't shy away from testing the best solution to solving a problem, right? So that attitude we should always carry, where I will be flexible and I will test new solutions and new solutions and things that I've never seen in my life. I will try them, right? And once you have that openness, and when you are choosing to relax your rigidity, there is no stopping you, and you will become the best in time for sure. And finally, thank you very much for all your attention. And one last request I have for you: if you are in this data science practice, and if you are a solutions provider or a problem solver, you should definitely have fluency in two languages. Every engineer should have fluency in two languages. One for scripting and rapid prototyping, which could be Python. Sometimes it could be R. I have not practiced R much. I've practiced Python though. And one for enterprise development. So the moment your solution is proved to be working fine, then you have to migrate. You should have the ability to migrate your solution into an enterprise type solution so that it becomes a product and people start using it, right? So I am of the opinion that Python is definitely not an enterprise language. Python can never be an enterprise language, right? But Python is amazing for rapid prototyping. You can build things very quickly. You can test your concepts very quickly, test your ideas, very quickly. But when it comes to enterprise deployments, Python is not the right language. So please always pick up a second language. It could be Java, it could be .NET, it could be Scala, but pick a second language which is meant for enterprise software development, so that when your solution sees the light of the day, it works perfectly without any problems, right? So please consider this as a request, and for all sake, please consider Scala as your enterprise language. And trust me, you will thank me for that. It's such a beautiful language. And with that, I thank you all. If you have any questions, I'll be willing to take it. Yeah. So what should I do now? If someone raises their hand, you can probably unmute yourself and ask the question.
May I just ask like that?
Go on.
Okay. So, sir, the thing is, doing the data science diploma in IIT program, I currently completed a course called machine learning techniques, where we learn things like clustering, regression,
Yeah.
classification. So we actually had hands-on sessions in which we coded using NumPy the different machine learning models.
Right.
We didn't use scikit-learn. So when we did use these things, when we did use make the models, we used for loops, while loops. We went for the procedural process.
Right.
So how do we actually transfer to the functional paradigm? I mean,
For starters, look for opportunities to use map. Right, the map function, right? So Python has this map function which allows you to execute a Lambda function on all the data points. See, what is your for loop doing? For loop is going through every data point and performing some operation on every data point, isn't it? So what you can do is you can rephrase the problem into a map job, where the task that you have within your for loop, construct a Lambda with that, and then pass the Lambda as an argument to the map function. You will get the same output, but your code will suddenly become smaller. Instead of several lines, your code will become much more smaller and elegant. So the first step is look for opportunities where you can convert a for loop into a map. Look for opportunities, and look for opportunities for applying other methods. So there are methods like fold, methods like reduce, methods like filter. Look for opportunities where you can force yourselves to follow functional style programming by using a lot of Lambda functions to finish your task. I think that is where you can start. See, it comes with practice only. So first is you'll have to do some reading about how to solve problems in functional style, right? There are books which allow you to do that, and there are a lot of tutorials online which will allow you to understand how to solve or how to approach a problem in functional style, right? If you do a little bit of reading and if you practice it in your labs and in your tutorials, then I'm sure in time you will pick up this trait very natively. So that's my answer. It is not like a switch you turn on, you become functional. No, it is not like that. It has to start from the way you conceive an idea in your mind, and how you break down that into your building blocks of your code and how you execute on them. So you have to look at samples of how to run the solutions in functional style. There are a lot of articles available online. Just spend some time with that. You will get the key. You will get the idea.
okay, sir. Thank you so much.
Thank you.
So,
Go on.
sir,
Go on. Yeah, you are audible.
yes, sir. So, my question to you is that you were like throughout the talk, you were mainly focusing on the fact that we need to bring the function to the data instead of the other way around, and that helps increase the, I would say, the speed and the computational capability, right? If I'm getting it correctly. So,
No, not like that. See, I'm not saying if you move the function to the data, it becomes magically faster. No, I'm not saying that. But some languages leverage that behavior to make your algorithms or make your implementation more faster. Languages like Scala will do that. Python will not do that. But if you want to, I mean, Python will not do it automatically. But let's say if you want to use multiprocessing or multi-threading in Python, your new style of programming where you have moved the method to the data, that style of programming will allow you to implement multiprocessing and multi-threading even more fluently. That is the idea.
okay. So when you say that we are moving function to the data, so I mean, it's not there was also the statement that you brought out, which was that when you convert the entire code into some kind of byte or machine code, so eventually both of them would look very similar. So, I mean, if you can just give a main idea of how these languages are able to do that, because I'm talking about from if I look into from a hardware perspective, so data will reside on the hard disk or the a drive or some other secondary storage device. So if I can't really get the function into the secondary storage because it doesn't have a CPU or a ALU or any kind of thing like that, right? So eventually the data has to come to the CPU. So how is the speed being leveraged in that situation? I didn't completely get that idea fully.
Yeah, sure. I see your point. Okay, I'll help you with that. See, the point is when you look at the machine code running at the processor level, there is no notion of object-oriented programming. There is no notion of functional programming. It is all procedural, right? Because the CPUs are still designed in one human architecture. You have to give a series of instructions, and the instructions are executed top to bottom. That is how CPUs executed. You know that already. Right. So at the CPU level, everything is procedural. We cannot do anything about it. But the idea of having levels of abstraction during the programming allows you for leveraging other benefits the runtime is offering you. For instance, as I said, in Scala, if you have a large data problem, if you have a large data set, and if you have a function which needs to run on all the data set, and if you frame it as a map job, the Scala runtime will automatically trigger multi-threaded environment to run the map job in parallel. As a developer, I don't have to do anything there. The runtime will pick and choose to parallelize it automatically. So that benefit is possible. That benefit is available only when I facilitate the compiler with functional style programming. Okay, but when the multi-threaded code gets translated into machine code, and when it is running at the processor level, depending upon how many threads, multiple ALUs will get engaged, meaning multiple cores of the CPU will get engaged. That is the only difference, right? If I had written my code, I'm sorry, what?
I mean, I'm just saying, okay, sir. I mean, I got it. So from what you said, is there any I did some OpenMP is there in C and C++, right? So I mean, is there a significant difference between what the two of them do, or is it like the programmer's effort gets reduced when we use Scala because it does it automatically?
No, see, OpenMP allows you to run application across different CPUs, different processes, right? Different processes, in the sense it will be running as different applications. So OpenMP is more complicated, and if you want to run your application on a different machine, and if you want to use applications across different machines, that is called horizontal scaling, right? That in such scenarios, OpenMP will help you big time. But what we are talking about as multi-threading is called vertical scaling. So there are two different ways of scaling. One is scaling your application across available CPUs in the same machine. That is called vertical scaling. I mean, let's say if you have 32 cores, and can I leverage all 32 cores in the same machine? That's called vertical scaling. But let's say I have configured 4 or 5 machines each with 16 cores. And can I leverage the core from a second machine, from the third machine, from the fourth machine? And that is called horizontal scaling. And horizontal scaling is something Scala will not give you by default. right? We have to take some extra effort to make it happen. OpenMP, OpenMPI kind of frameworks allow you to scale horizontally, and they also allow you to scale vertically. Okay, so we are comparing apples to aeroplanes here. So scaling across CPUs, multi-threading only allows you for vertical scaling, which means you can spin a thread in the same machine. You cannot spin a thread in a remote machine.
Okay,
Right?
sir. Okay. Yeah.
So we have to understand the difference here. And there is one more level of craziness is there. So if you look at frameworks like Spark, it allows you to run applications across a cluster of, let's say, 1,000 nodes or 500 nodes. It allows you to scale like that, horizontal scaling at crazy levels. So Spark-like frameworks will allow you to do that. They go beyond OpenMP and OpenMPI.
Okay,
They
sir.
go beyond
Okay.
that, right?
Okay.
So we have to choose the framework appropriately based on what type of scaling we want to implement. The simplest scaling is multi-threading, which is vertical scaling.
Okay, sir. Okay, sir. Thank you so much. And like, I just had another short query, if you're not running out of time, which is like, for usually in deep learning, like we have a set of like maybe convolutional layers or like RNNs being processed one after the other, sequence to sequence model. So in that case, I think the data independency in some sense would be violated, right? So is it advisable to, is there a way we can probably use such languages in a framework where we do deep learning? So is it possible, sir? Like,
It's already there. See, the thing is, Python, TensorFlow, or let's say Torch-like frameworks are meant to do that. What they do is, instead of using CPUs, they leverage the multiprocessing available in the GPUs. Right, so GPUs like, let's say, 3090 or the likes have like several. They have like 12,000 cores. It's like 12,000 CPUs running the job. Right, such GPUs have so many cores, and you divide your data problem into chunks of 12,000 blocks, 12,000 different chunks, and run these 12,000 blocks in parallel. Such ability is available in GPUs today, and that level of parallelization is supported by frameworks like TensorFlow and Torch. So what we are discussing today is CPU level parallelization, but GPU level parallelization is another level of scaling, But if the data independence assumption is broken there, that is when GPU leverage becomes not very useful. Because see, when data dependency problem is non-existent, then GPUs can be leveraged in full. But if you frame your problem in such a way that the data dependency is already always there, then GPUs cannot be used because of the dependency issue. It will run in sequential form, and GPU even if I use GPU, it is not going to serve me any purpose. So that is where these frameworks like Torch and TensorFlow, they divide the problems into smaller subproblems, and they parallelize the subproblems which don't have dependency issues, and they run the remaining subproblem sequentially in the CPU. They jump between CPU runs and GPU runs. That is how they solve the problem. Right?
okay, sir. Okay. Thank you so much.
To your example, CNN will nicely work with parallelization because majority of the filters can be run in parallel. The problem with RNN has dependency issues because you cannot train another round. The time distribution can become a problem because it operates on the previous iteration output. So that's why RNN training is painful. CNN training is amazing. Convolution neural network training is amazing because most of the problem can be treated as a data parallel problem. In RNN training and LSTM training, the problem is sequentialized because of the very design of those networks. That's why training an RNN and training an LSTM will take more time. And give you a connotation, LSTMs were eaten away by transformers only for that reason. Right? Transformers allow you for parallel processing. I mean, it does more processing, and it can process everything in parallel. And transformers completely washed off LSTMs because LSTMs were hard to train. Not hard to train, it takes longer time to train, whereas transformers can be trained fairly fast because of the inherent parallelization abilities. So parallelization is the key, my friends. because you're dealing with large data. You have to think about parallelization as one of your strong constraints.
Right. Okay. Thank you, sir. Thank you so much.
Thank you. Are there other questions?
Sir, good evening, sir. Thank you very much, sir.
Thank you.
I do not have a question itself. Just a request for your comments on the new programming Mojo, sir. Will it replace Python? And that's my doubt, sir.
Which language is going to replace Python?
Mojo, M-O-J-O, Mojo, sir. I'm just asking.
Okay. So there is one language which is a potential replacement for Python called Julia. That is the only thing that I have heard of, which is seen as a potential descendant of Python language. But Mojo is probably more recent. I mean, I'm yet to practice that, so I don't think it is going to replace Python anytime in the near future.
Yes, sir. Yes, sir.
So don't worry about it. Yeah, Python
Yes,
is
sir.
here. Is here to stay.
Thank you, sir. Thank you very much.
Thank you.
Thank you, sir.
Are there other questions?
Hi, sir. Thanks for the session. I have a quick question here.
Sure.
I have interacted with many of my friends and teams in the organization as well. But predominantly, I heard that they are using Python for data science. But is that like Scala will also be used for data science, or why I'm not hearing much like Scala is being used for data science?
See, I told you Spark is a framework which is fully implemented in Scala, right? And Spark is used for big data processing, big data analytics, large scale machine learning, large scale data science deployments are all running on Spark framework.
Yeah.
Right. So Scala is a language designed for scale. So that is why they named it as Scala.
Okay.
It's a language designed with scale as the primary constraint. I mean, how do I scale my solutions to large volumes of data? That is how the design of the language itself was constrained by. So, see, the thing is, Scala is a language which is not very popular amongst developers because Python is more popular. Very simple, because Python is easy to grab and a lot of libraries are already available, and you can create something very, very quickly in Python. That's why I said it is an amazing language for rapid prototyping. But the problem is it will be just a prototyping language.
Okay.
Right? If you are serious about enterprise deployments with very, very hard constraints, Python will not survive those constraints, those conditions. It cannot survive those conditions. See, a simple example I'll tell you. The memory management in Python is miserable for enterprise deployment.
Okay.
The amount of Python has this internal memory management, right? Because it is a weakly type language, so you can use any data, any variable name for any data type, and you can change the data type on the go. A lot of things are there. So the memory management within Python is so hard, so complicated. You don't know when your memory will be freed.
Okay.
Right. So that's a big problem in enterprise setting, because in enterprise setting, you will be working with very, very strong constraints on resource usage. And if the runtime is randomly consuming resources, and people are going to hate it.
Okay.
But the guys who maintain those servers will hate to maintain such systems because of this uncontrolled behavior on resource utilization. It's a pain, man. Seriously, it will be very difficult for the DevOps guys to manage those systems, manage the resources on those systems. So that is why I'm saying, for serious enterprise deployment, we have to consider serious enterprise languages, because those languages are designed with resource constraints in the design itself. Python is not designed for resource constrained implementation. It is designed only for rapid prototyping.
Okay. Thanks, sir.
Sure, thank you. See, I'm not saying Python is a bad language. Python is an amazing language for quick prototyping. But when it comes to enterprise deployment, please know that Python is not designed for enterprise deployment. Please know that. That's all. Take the risk. Because sometimes we will take the risk. Until I'm ready with some enterprise quality software, I will use my Python proxy. No problem with that strategy. No problem with that strategy. But be prepared for things to break and be prepared to go and patch it. So that is all. The second biggest problem with Python deployment is your code cannot be protected. The source code is visible, no?
Okay. Yeah.
A big problem. See, if I give you my proprietary algorithm to you in as a Python package, how will I protect my source? It's super hard. Even if I Dockerize it, it's very hard to protect the source. So there are some nuanced challenges with Python deployments. Nuanced challenges. So just use the right language for the right use case. That's what I will say.
Okay.
Thank you. Yeah. Are there other questions? Excellent.
Okay. So, sir, thank you so much. Like, it was a very great session, and we all are privileged to hear you. And we hope for such more sessions in the future with you, sir, and learn more from you. Thank you so much, sir.
Absolutely. It was a pleasure. Thank you very much. Thank you. Have a good day. Thank you.
You too, sir. Thank you.
Thank you. Bye-bye.
Thank you, sir.